Welcome. Today we're going to be looking at the notes worksheet entitled Reference Angles. And this just picks up exactly where we left off on the previous notes worksheet. If you remember correctly, we talked about what can be a reference angle. And let me be very clear again, a reference angle is always acute and always positive. So that's what a reference angle is just by definition. And then we're going to see a connection between the reference angle, what we're going to call theta prime, and our theta as it rotates around either clockwise or counterclockwise. And I think I'd mentioned this is kind of the last, what I would call a preliminary lesson before now sort of taking the turn on the next piece and shifting our curriculum a little bit. So let's see if we can get some good stuff together and put some things that we've talked about kind of together dealing with these angles. Okay, well let's get started right away. It says positive angles and reference angles determine the relationship between theta and theta prime. Okay, good. So everyone, I think we've kind of done this before. A lot of these sketches over this course. So let's get 4 coordinate planes squared away there. When you get an opportunity, just give me a quadrant 1 angle, quadrant 2 angle, quadrant 3, yeah, let's get that in there, and then quadrant 4, just something like that would be fine. And again, basically I'm going to just do a standard counterclockwise rotation, trying to get to my terminal side right away. So I guess I would say that's theta right in there. And if you get an opportunity, by the way, let's draw those terminal sides in too. The drop in the perpendicular there. So let's go with that, our theta. And again, just kind of thinking out loud with this, let's go ahead and get that right in there. And let's see, let's do that as our theta and get that going to the horizontal axis. If you remember on the last one, we kind of ended the lesson on talking about how to get the theta prime in place. And we do want to go from the terminal side perpendicular to the horizontal axis, just like that. Okay, so I've at least set it up. Maybe slightly out of turn here, but I think it should still work, because now what I need us to do is throw in our theta primes for each of those 4. And if you remember, the reference angle, in terms of the visual aspect of it, is always in between the terminal side and the horizontal axis. So for quadrant 1, and I think this should make sense, theta prime is theta. So I just put a little slash right here. Theta prime and theta are the same. Quadrant 2, that's going to be your theta prime right in there. Quadrant 3, that's going to be your theta prime right in here. There's your theta prime, always acute, always positive. In quadrant 4, I think that's going to be our theta prime right in there. Terminal side, horizontal axis. Again, sort of an acute angle in a right triangle. Okay, now what I'd ask you to do is almost pause the video for a sec and talk to me about the relationship between theta and theta prime. And I guess there's a reason there are 2 blanks here. So you're going to do this basically. How are you going to get theta prime if I give you a theta? And I'll tell you why there are 2 blanks in just a second, but let's go ahead and fill that in, just so you know what I'm looking for, and then maybe you can start that out yourself, or you can wait on me. Totally your call. All right, now the reason that there are 2 blanks is basically 1 for degrees and 1 for radians. And so what I'd ask you to do is just see if you can come up. If I gave you a theta, could you calculate theta prime for me in each of the 4 quadrants? Can you give me a little rule of thumb in each of the 4 quadrants? So pause and give it a try. Well, let's see how you did. Well, I think I gave this one away, not that this comes up a ton, but theta prime and theta are the same in quadrant 1. Absolutely. Now here's what's interesting. In quadrant 2, here's the rotation for theta, here to here. I want this piece right in here. I'm hoping you kind of saw that really it's almost like a 180, like a half rotation around. If I take the if I take the 180 and I subtract away this theta right here, I'm left with just this little piece right in there. So what I wrote on my paper is it seems to be 180 degrees minus theta. And this works for any quadrant 2 angle, by the way. In radians, it would just be pi minus. Now this is a good one right here. So here's theta, and I just want this piece right in here, the way I'm seeing the rotation, everybody, is theta is all the way there. What happens if I took all of that theta and subtracted away the 180, just above this x-axis here, this 180? I should be left with what's in here, that theta prime. So instead of 180 minus theta, I'm hoping you guys all see it's theta minus 180. Take the entire angle, subtract 180, and that should give me that little reference angle right in there. Okay, and of course, in radians, that would be it right there. Okay, last one. How am I going to get this little guy right in here, that theta prime, for a quadrant 4 angle? Well, what I saw is that it is the full rotation around, the full 360. If I take my full 360 and I subtract the theta from here to here, should give me what's left right in there. So I'm hoping you saw that as well, but 360 minus theta should do it. And remember, 360 in radians is 2 pi, of course. So again, just little rules of thumb to get us thinking about it. I'm going to give you a bunch of thetas. You're going to have to be able to pull off theta primes. Well, a lot of drawing, a lot of visualization that goes into this course. So let's start talking about a reference angle. So it just says sketch, name, reference angle. Sounds good. So I guess here's what I'm thinking of. Let's go ahead and just get 135 degrees right in there. Everybody give me a rotation if you would, 135. And give me a little theta prime right in there. So there's theta prime, of course. And I'm hoping you would see, and what I'm looking for very simply is what theta prime is. Just look at the top of the page, of course. It's a quadrant 2 angle. And I'm hoping you can see this here, that if I really wanted theta prime, I could probably just take 180, subtract the 135, and I get 45 degrees. And again, do you think it's any coincidence here that we've always talked about 135 as a multiple of 45 degrees? No, I mean, it's not a coincidence, of course. These two things are going to go hand in hand. And what we're going to see is all the trig ratios on the reference angle correspond to the trig ratios on the 135. We're going to see that in action just very soon. So, by the way, with what we're going to learn here today, it's not necessarily reinventing anything. There's some cool stuff with it, but it's basically just really complementing all the things we've talked about thus far with the unit circle and right triangles. Just really working with that. So if you know all that stuff really well, this shouldn't stress you out. Okay, well anyway, this one we don't have a rule of thumb, but here's negative 120 from here to here. Here's my theta prime. And so think about that for a sec. What do you think theta prime would be? Again, it has to be acute and positive, and it's got to be that angle between the terminal side and the horizontal axis. Well, it looks like I went 120 degrees. Probably have to go another 60 to get to that horizontal axis. And again, don't worry about the rotation. It's always positive. So 60 degrees. Excellent. Let's see, 7 pi over 6. There it is right in there. There's your theta prime. And there's your 7 pi over 6. And you could do, again, in this case, what we would do is 7 pi over 6 minus pi. But I think you would hopefully be in agreement with me. And, you know, basically what we have found is that working in these fractions, all of those are just multiples of the reference angle, either a pi over 6 or a pi over 4 or a pi over 3, whatever the case may be. So that's the beauty of reference angles with all of these good special angles in radians. Whatever pi over 6 this is, the reference angle is just pi over 6, which probably leads me into part D. No matter what pi over 4 we're talking about, in this case it's 7 pi over 4, which happens to be this right here. So that's 7 pi over 4. Really doesn't matter. If I want that reference angle, the reference angle for any pi over 4 is going to be exactly pi over 4. That's kind of nice. These last two, just depends how we want to do this. 2.3 radians here. This is an interesting one. If I was to look at 2.3 radians, probably would be somewhere up there, give or take. Again, doesn't have to be perfect. Should be able to ballpark it, though. And then here is my theta prime right in there. And so if that's my theta prime, well, I would just look at the top of the page and get my rule of thumb. And in this case, if I'm in radians, all I want to do is take pi and minus my theta, minus my 2.3, and this would give me that reference angle right in there. Now, if you really, really wanted to, I'm wondering if I have this. I actually don't have it on my sheet, but if I really did want to go ahead and figure out what that decimal approximation would be, well, let's see, pi minus 2.3, and you can see it's about 0.8416 or whatever you want to do there. I only went one decimal place here, so, but whatever, I'm going to go a little further. So something like that, roughly that many radians. I like this one a little better, to be honest. That's the exact form. Okay, and then the last one here before kind of taking the next step forward, 6 radians, everybody should be able to visualize 6 radians. There it is, just before 2 pi radians, of course. So that's 6, and hey everyone, there's your theta prime right in there. What would be that angle, of course? Well, let's see. So theta prime equals, if you look at the top of your page, all I have to do is take the full rotation and subtract away theta. And so, you know, that would be the theta prime precisely, 2 pi minus 6. And again, what you're going to see is basically all the trig ratios of theta prime are equivalent to the trig ratios on theta. We're just going to be careful of positive versus negative. Okay, good. Well, let's move forward here. I guess, wrote a couple strategies, a couple ideas which we'll incorporate. So it says, this falls under the heading of using the reference angles in order to evaluate trig functions at theta. So find the function values at theta prime. So if I know sine or cosine or tangent of theta prime, then I'll be able to find sine and cosine and tangent of theta. And so it says use the quadrant in which theta lies to attach the appropriate sign, either positive or negative, to our numerical value from the first step. So this might look just like a whole bunch of verbal jargon at this point, but let's see if we can put this together nicely with some examples. So I think the development piece to this is going to be over, but let's see if we can put some stuff together. Now again, I'm not trying to reinvent anything here. If you can pull this off, great. So here's the idea. And if you know the sine of 135 degrees without going through all this hoopla, that is absolutely perfect. You have the unit circle. You have some other ideas from right triangles, which is, as a matter of fact, what we're going to incorporate here. But you should basically know the sine of 135 degrees. But it's important to really put things together and really make sure you're seeing the connections, the stepping stones, so to speak. So let's go ahead and pull this off. And here's, I guess, what I would ask. The first order of business would be to take a look at 135 and figure out what the reference angle would be. And I hope you would all be in agreement that 35 is really a multiple of 135 is a multiple of 45 degrees. And so here's the idea. Based on what we did, and we actually constructed this, you should be able to tell me the sine of 45 degrees. And based on all the relationships, and wouldn't need the unit circle, you just need the right triangles, and as I said, you have to know it one way or the other. You have to know sine of 45 degrees, and it's root 2 over 2. So with that, what this is basically saying is that the sine of 135 degrees is the same numerical value as the sine of its reference angle, the 45 degrees. We just have to be careful of positive versus negative. So I'm just going to go back up here and say, all right, well, sine of 135 degrees happens to be in quadrant 2. And in quadrant 2, sine is positive. And so as a result, sine of 135 degrees is root 2 over 2. And that's just a way to connect these pieces. Now, if you know your unit circle, and you know that the sine of 3 pi over 4, which of course is 135 degrees, you know that the sine of 3 pi over 4 is root 2 over 2. End of story. You've got it. Again, this is just another way to connect a variety of things to put it together in case you really don't know your unit circle. Okay, well, let's continue. Let's try a couple others. So, 120 degrees, everybody. 180 minus 120 is 60. Beautiful. Now, this I can't help you with. You have to be able to know this piece. You have to be able to visualize the cosine of 60 degrees with this. And the cosine of 60 degrees is exactly 1/2. Now, that means that the cosine of 120 numerically is 1/2. I just need to figure out is it positive or negative. And so I would say, okay, well, 120 is in quadrant 2. And in quadrant 2, cosine is negative. And so as a result, everyone, cosine of 120 degrees is negative 1/2. And that's a way to talk yourself through those ideas. On the unit circle, everybody, cosine of 2 pi over 3, it's negative 1/2. Of course it is. Let's do one more here and then keep going. 225. Oh, good one here. We have always seen 225 as a multiple of 45. Absolutely. And we do know the tangent of 45 degrees. We constructed it using a right triangle where the opposite over adjacent is 1. Tangent of 45 degrees is 1. So now I'm thinking about that 225, which is in quadrant 3. And of course, good stuff right there. Just don't forget, tangent is positive in quadrant 3. And so as a result, everybody, tangent of 225 is 1. Excellent. Now, example 3 it's kind of a weird one, but I just wanted you to see it with some other angles as well. I know you can type in cosine of 211 and be done with it, but I want you to see the connection with the reference angles. I think it'll help us on the last couple examples of the day here. So here's what I'd ask you to do. Think about it for a sec, or pause the video for a moment, please, and come up with a reference angle for me for 211 degrees. So since it's in quadrant 3, you would take 211 minus 180. 211 minus 180 is 31 degrees. Now what I'm going to do is just kind of use the idea here. So cosine of 31 degrees is about, we don't have the exact value for this, but let's go ahead and grab the calculator, and I'm going to just make sure I'm in the right mode, and I'm not. So I'm going to go degree mode, and I'm going to type in cosine 31. And so to about 4 decimal places, I got about 0.8572. Okay, good. 0.8572 for the cosine of 31 degrees. Now what that means, everybody, is that the cosine of 211 is going to be the same numerical value. It is in quadrant 3. 211 is in quadrant 3, and cosine is negative in quadrant 3. And so as a result, based on what you see right here, I should be able to type in cosine of 211, and it should just be the negative of that value right there. And we are obviously going to see if that is the case. So let's type it. Cosine 211, magic. Perfect. Again, I know we could have typed it in right away and you would have seen it. I just want you to see the connection with the reference angle, that's all. Okay, let's go ahead and do this one right here. So theta prime, everybody, it is in quadrant 2. Everyone, 180 minus 168 is 12 degrees. Okay, now, here's what I'm going to be after. The sine of 12 degrees. And I'm going to pick my calculator up again and type in sine of 12 degrees. Okay, so I have about 0.2079. Perfect. So now I know about the cosine of 168, everybody. So, I'm sorry, sine of 168. We are in quadrant 2. What do I know about sine? Oh, it's positive. Absolutely. Quadrant 2, sine is positive. So I will momentarily check, but the sine of 168 degrees should be 0.2079. And let's go ahead and verify exactly that piece up here. So sine 168, and notice it's the same. Okay, good. Hopefully it's starting to fire on all cylinders here. Let's take a look at this piece. So without a calculator, what I want us to determine is, are these values the same? Are they opposites of one another? Or are they just totally numerically different? So let's take a peek. It's all based on the reference angle. That's the concept, is if it has the same reference angle, the ratios are going to be the same. All 6 ratios are going to be the same. It's just the positive versus negative that you have to deal with. So let's start out with reference angles, everyone. In this case, it's in the first quadrant, so it is, of course, 70 degrees. I'll just write that right there. Now, everyone, I'm going to go ahead and take a look at the theta prime for 110. And guys, 110, second quadrant. Let's take 180 and minus the 110, and should be 70 degrees also. Which means numerically they're going to be identical. Now I just have to determine, are they going to be the same, or are they going to be opposites from one another? So guys, 70 degrees, we all know is in quadrant 1, and sine is positive in quadrant 1. 110 degrees, everybody. It's in quadrant 2, and sine is positive in quadrant 2. And so as a result, sine of 70 and the sine of 110 should be the exact same. Again, I'm going to ask you to do these without the calculator there. Now, I'm going to just sort of do this on one coordinate plane. You don't have to do this on your paper, but 70 degrees, give or take, would be something like that. And the idea being, if that's 70 degrees right in here, here's the y, and here's the r, of course, right? You would calculate that, and for 70 degrees, it's equal to one particular number. Now, let's take a look at 110. 110 would be right there, give or take, just reflected over the y-axis, basically. And take a look if I drew, same thing, the y to r. Does it look like the y to r ratio would be identical right there? Absolutely. And notice, both positive y's, obviously r is always positive, so they should be the same. And so if they're in the same position, so to speak, just different quadrants, they're going to have the same ratios across the board. So let's see, sine 70 and sine 110. And remember what these ratios mean. If you were to take the y over r at 70 degrees, the vertical over the direct, so to speak, it's always going to be this number right here. Okay, good. Let's try the next one. 130. Let's see, 130 is in the second quadrant. I'm seeing 180 minus 30. That's 50 degrees. Okay, let's see. Let's come over here. 230. So that's in the third quadrant. 230 minus 180 is also 50 degrees. All right, so position-wise, they're identical. Just quadrant-wise, that's what we're going to look at. So again, I would go back to this. Quadrant 2, sine is positive. Quadrant 3, oh, wait a minute, sine is negative. Same reference angle, but different signs on those, opposites. Absolutely. And again, you don't have to draw if you don't want to. Here is 130 degrees, something like that. Here is 230 degrees, something like that. Sine would be the y to r. Oops. Let's get rid of that. Don't know why that popped up. Sorry about that. So the y to r. Here's the y. Here's the r. You can see they're in identical positions. Just one y is positive, the other y is negative. All right, last one here, and then we'll get example 5 taken care of. How about this one? 250. This is an interesting one right here. I'm seeing 250 as, let's see, we would take 360. Oh, I'm sorry. We're in quadrant 3, my fault. So quadrant 3 there. So 250 minus 180, I'm seeing that as 70 degrees. And then 340, there's my quadrant 4. I got mixed up there for a sec. 340, so let's do 360 minus 340. That's the little rule that we had at the beginning of this lesson. And this would be 20 degrees. And right away, since they are not the same reference angles, these are just completely different. They're just in the wrong positions. They're different positions, so different ratios, of course. So let's take a peek just visually. Here's the 340. Here's the 250, something like that. Look at the x to r here, everybody, and look at the x in relation to the r here. You can see this x to r is just bigger numerically than this x to r. Here's a smaller horizontal to the radius. Here's a bigger horizontal to the radius. So I would bet numerically 340's cosine value is bigger than this one right there. And let's take a peek. Can't hurt. So what did I say? Cosine of 340 numerically is going to be bigger than the cosine of 250. So pretty large number there. And if I did cosine of 250, probably a smaller numerical value, of course negative, but as you can see also smaller numerical value. Okay, again, hopefully it's really starting to work for you and you're starting to see all these things in action. Okay, last one. So example 5, let's see if we can do A, B, and C, and let's start them out here. So it says fill in the blank with an angle measure in between 0 and 360 degrees. So the sine of 81 degrees is some ratio. There happens to be another angle between 0 and 360 that has the exact same sine ratio. Let's find it. So let's start it out here, everyone. I'm hoping, again, you've seen now, it's all in relation to reference angles. So theta prime is 81 degrees. Also, I know that 81 degrees is in quadrant 1, and I know that the sine of anything in quadrant 1 is positive. All right, so now everybody, I'm going to kind of reverse the process here. In this case, quadrant 1 produced a positive sine ratio. Where else is sine positive? Well, sine is positive also in quadrant 2. So this tells me that this angle right here has to be some number in quadrant 2, and that the theta prime has to be 81 degrees. So we can do this a couple different ways. But I guess I would kind of go back to this piece right here. I'm just going to do this. You don't have to. But in quadrant 2, we said that theta prime is always 180 minus the theta, right? That's how we got our theta prime. Well, in this case, everybody, I know theta prime. I just don't have theta. So let's see this work. I know that that's 81 degrees. And this is going to be 180 minus theta. And there are so many different ways to see it. If you don't like my formal approach here, that's fine. I would maybe bring the theta on over to the other side, make it positive, and then subtract the 81 degrees. But I think you would see if you do 180 minus 81, you should see 99. So I believe 99 degrees is the angle in quadrant 2 that has this as the reference angle. So actually I'm going to write that here. Theta prime did have to be 81 degrees. Well, let's check it out. The nice thing about these, and you know, you're going to see them plenty of times, the nice thing is anytime I give them to you, you have a calculator to just check. There's sine of 81, here's sine of 99, and it's the same, of course. Cool. All right, let's go get letter B. So let's start it out. Same process, everyone. 100 degrees. Well, still quadrant 2. A lot of these are in quadrant 2, just coincidentally. 180 minus 100, everybody, is 80 degrees. There's your theta prime. Okay, now I'm in quadrant 2. And in quadrant 2, everybody, cosine is negative. Okay, good. So now let's reverse course. Over here, I know that I need a negative cosine value. Cosine is negative also in quadrant 3. You could really see how all this comes together, all these last several lessons working out nicely together, all connected. And theta prime is 80 degrees, and I'm in quadrant 3 as a result. So let's see, how did we do this in quadrant 3? Well, we said that to get a theta prime, we take our theta, and we minus 180. Now again, if you could figure this out without my formalities up here, that's fine. But there is some angle in quadrant 3 that has theta prime as 80 degrees. However you find it, it's fine by me. So that 80 degrees is really theta minus 180. And I would probably bring that on over. And I'm seeing this, everybody, as 260. And we're obviously going to check momentarily there. Make sure everything is correct on that. But let's see. So I do cosine 100, and then cosine, what did we say, 260, and notice it's the exact same value, both negative. All right, one more, kind of wrap this on up. So here's what I have, everybody. Now I've got sine of 70 is equal to the opposite of two different sine ratios. So let's walk ourselves through this piece. So opposites, 70 degrees, of course. There you go. That's your theta prime. We're in quadrant 1, everybody, and sine is positive in quadrant 1. Now, in this case, I want the opposites. So I'm thinking we want negatives here, because sine is positive in quadrant 1. So I'm looking for a negative in quadrant 3 for sine. Or, everybody, where else is sine positive? I'm sorry, where else is sine negative? Been a long lesson for me, apparently. So sine is negative in 3 and in 4. So there's an angle in quadrant 3 that we want. There's an angle in quadrant 4 that we want. Both of which have theta prime as 70 degrees. So everyone take a moment, if you would. Pause the video and try the little quadrant 3 idea and try that little quadrant 4 idea and see if you can get it to work. So take a moment and then we'll see. Okay. Well, I got these two answers here. When I did basically, I took my 180 and added 70. I ended up getting 250 as the quadrant 3. And then I did 360 minus the 270, and I ended up getting 290 degrees on that. So see what you have on your paper there. And if you didn't get this one quite right, just ask and we can take a look at it together. I just incorporated the same ideas from above. Let me verify one last time, and then we will call it here. So sine of 70 degrees, there it is. There's your answer. Now we should be able to see that the sine of 250 is the exact same number, opposite. Sine of, what did I say, 290, same thing, everybody? Same number, it's opposite. Okay, good. So it's really, at this point, understanding really some of those special values, understanding the 6 definitions, and really understanding the behavior of those functions as our angles change in either degrees or in radians. Well, as usual, everyone, thank you very much for listening. If you have some questions, let me know. And get some practice on this, please.